Hello, I am Alexandra, a PhD student from Portugal. My PhD project is about quantum amplitude estimation using noisy quantum devices. In this video, I will be presenting the poster that I submitted to TQC on the impact of decoherence in quantum amplitude estimation algorithms. Quantum amplitude estimation is closely related with Grover's algorithm and capable of the same quadratic speedup. The difference is that while Grover's algorithm seeks to find some special item, quantum amplitude estimation seeks to estimate how many such items there are. This can be generalized to a continuous domain, so that we are learning amplitude associated with a basis state for some wave function. So if we have a superposition of the computational basis state 0 and 1, we could use amplitude estimation to learn the probability of, upon measuring, obtaining state 1. Basically, this problem can only be solved one way, by repeatedly sampling outcomes and estimating the probability of measuring 1 as the observed relative frequency for this outcome. The task amounts to determining the parameter of a Bernoulli distribution by sampling from it. The part where quantum approaches can stand out from classical ones is that quantum interference allows us to amplify the state of interest. In Grover's algorithm, this amplification process is used to maximize the probability of success. In amplitude estimation, it comes in handy as well, but now for a different reason. We don't just want to maximize the probability of success, so instead we work a little differently with the amplification operator, the operator implementing one Grover iteration. As it turns out, we can deduce the amplitude from the eigenvalues of this operator. All we need to find this quantity is to perform quantum phase estimation on the amplification operator, and then we can deduce the amplitude from the values that we obtain. This was the first proposed way of realizing quantum amplitude estimation, and it gets us the full quantum advantage, quadratic speedup that I mentioned before. The problem with this textbook approach is that it's much too demanding for present-day quantum hardware, whose many shortcomings severely limit what we can compute and how long we can take to do it. So, for now, implementing quantum amplitude estimation as it was first proposed is a reality for a distant future, at least for problem sizes of interest. This raises an interesting question: what can we do to bring this future closer? Can we change the algorithm to make it more accommodating to our experimental flow? What degree of imperfection can we tolerate while still having a quantum advantage? Is it possible to achieve some degree of quantum enhancement in spite of noise? In recent years, several approaches have been proposed that answer these questions affirmatively. This is very interesting because quantum amplitude estimation finds applications in many practical contexts, namely expectation value estimation, machine learning, and numerical integration. The trick is to use quantum amplitude amplification differently. We can think of it as a trick, allowing us to change the value of the effective amplitude, by which I mean the amplitude associated with the amplified wave function that we can measure. So instead of, as in the classical case, being limited to a single and rather boring experiment, we have an extra degree of freedom to exploit how much to amplify before measuring. There are many such algorithms, all of which follow this basic template. We prepare a superposition and amplify, and then measure, getting some data. Then we start over. We prepare another superposition from scratch, amplify to a different degree, and then we measure again. And we repeat this as many times as necessary. As for the resulting data, we can process them all in the end, in a batch processing step, or we can process them sequentially, in which case we can use them to inform the following iteration via a feedback mechanism. These approaches are very different from the quantum Fourier transform proposition, but interestingly, it has been shown that they can not only achieve substandard quantum limit performance, they can actually attain the exact same quadratic quantum speedup as the phase estimation approach. This means that the advantage is not intrinsically tied to the quantum Fourier transform. Instead, it springs from the ability to observe the system at different stages of amplification. Importantly, this amplification does have a cost, but even when that cost is considered, quantum-enhanced observations can be more profitable than the classically achievable ones. Of course, there are a couple of questions left to answer. The template that I gave does not fully specify the protocol. How much exactly should we amplify before each measurement, and how should we process the resulting information? There have been many interesting proposals which differ in how they tackle these 2 points, and they each have their ups and downs. This graph presents the numerical performance of a selection of them, with the estimation error plotted as a function of the number of queries to the quantum oracle. The faster the decrease, the better. These are the results of noiseless simulations. The red squares are the classical case, and the standard quantum limit, the fundamental limit when using purely classical resources, is parallel to it. The gray circles are the quantum case, using the textbook algorithm. The evolution of the data points is parallel to the Heisenberg limit, the fundamental limit of metrology which can be achieved using quantum resources. All other strategies fall somewhere between these two limits, representing different degrees of quantum advantage, full, partial, or none. They also have different vertical offsets, which mean that different constants are involved in the cost, and also different classical processing costs, a metric which is not represented at all in this graph. Another important aspect of an algorithm's performance is its response to noise. We can make a graph similar to the previous one, but now considering a finite coherence time for the quantum device. We can see that different algorithms respond very differently to this change. Importantly, once noise is introduced, an algorithm with better idealized behavior may actually do worse than another otherwise beneath it. Some algorithms are even unable to terminate in the presence of noise, and different strategies are affected differently by different types of noise. In this sense, it is pivotal to analyze and even develop algorithms having noise considerations in mind. And that is the key takeaway I want to present with my poster: the importance of the differences between quantum amplitude estimation algorithms beyond asymptotic performance. Some algorithms are rigorous but impractical, while others are empirically successful but less theoretically sound. Some have perfect asymptotic behavior but large overheads, while others have worse complexity but much better constants. Some require adaptivity and some do not. Some require lots of classical processing, while others require very little. Some are resilient to noise and some are very susceptible to it. As new algorithms are proposed, or old ones modified, we can hope that better trade-offs can be achieved between all of these points. That's it. I hope you learned a bit about quantum amplitude estimation. If you want to chat more about it, meet me at the booster session at TQC or send me an email at alexandra.alves@inl.int.